Greetings, y'all. Dave here.
And Jeanette with your topic 4 review for when you need to cram for your IB test tomorrow.
That's only the sad truth. Now, topic 4 chemical bonding and structure. Something important. Something important to keep in mind as you're going through this unit is intermolecular forces versus intramolecular forces.
Intramolecular force is any force that binds together the atoms making up a molecule or compound.
Meanwhile, intermolecular forces are the forces which mediate interaction between molecules, including forces of attraction or repulsion which act between molecules and other types of neighboring particles.
If you look here, we've got ourselves a molecule. You can see that together, these two atoms make up a molecule, and they're intramolecularly bonded.
Then these molecules are intermolecularly attracted to other molecules. See the difference?
These forces are called van der Waals forces and include dipole-dipole forces, London forces, and hydrogen forces. Now moving on to the fun stuff, an overview of the 7 types of chemical bonding. Moving on to the first one, which is ionic bonding.
Hello! Yes, ionic bonding. An intramolecular bond. For this scenario, we'll say emerald, this block, are positive ions, and diamonds, this block, are negative ions, and they're stuck together in a lattice shape like so, like a strong type of bond due to the electrostatic forces of attraction between the oppositely charged atoms, resulting in a stable molecule made up of 2 ions. An cation has a positive charge, and an anion has a negative charge. Ionic bonds are omnidirectional, bonding in all different types of directions, and due to its strength, it's hard to pull the individual atoms out of the lattice. Like so, we may pull this out, the diamond block, but as you can see, the lattice still remains intact. And then it can come back. But ionic compounds are so strong, they have a high melting and boiling point, as they take a lot of energy to break. As you can see, I'm lighting all this on fire, but nothing's really happening. So, if we do something that has a little bit more energy, like so, then they'll break. So an example is kaboom. An example of ionic bonding is with sodium and chlorine, where sodium atoms each lose an atom, forming each lose an electron, forming cations, whereas chlorine atoms gain electrons to form anions. These ions are then attracted to each other in a 1-to-1 ratio, like you can see here. It's like a little dog giving a bigger dog a bone, and because of that, they hug.
It's also like this nifty portal here. As you can see, we'll make this the chlorine with 7 electrons, and this here is the sodium with 1 valence electron. So if we just take this guy and go over here, bond them together, there you go, you have a bond. Well, I love the analogy, Dave, but now to move on to nonpolar covalent bonding. Covalent bonds are bonds where atoms share an electron pair. This is unlike ionic bonds where one atom completely transfers an electron to another electron. Or atom to another atom. Instead, the 2 atoms come together to complete both of their outer shells with full shells of valence electrons. Nonpolar covalent bonds, which are different from polar bonds, are where both atoms have the same electronegativity and equal attraction to each other, and therefore have equal sharing. Imagine these 2 dogs over here, and that they have equal strength. So, if I were to give one dog a bone, this dog wouldn't be stronger than this dog, and this dog wouldn't be stronger than this dog, so neither would be able to pull it away from the other. Instead, they would both just sit there with half a bone in their mouths.
Amazing, Jeanette. That brings a tear to my eye. Now, if you would just come over here by doing like a so.
Oh, yep, here we are.
Next up is polar covalent bonding, yet another intramolecular bond. Polar covalent bonding is basically like a covalent bond, like so. where between atoms, where the electrons forming the bonds are unequally distributed, like over here, and because of this causes a slight dipole moment. Now, a slight dipole moment is a situation where one end is slightly positive and another end is slightly negative, which makes it polar. Now, polar covalent bonds form between atoms with electronegativity difference of about 0.4 and 1.7, and typically form between two nonmetals, which meets the electronegativity rule. Typically, polar covalent bonds form between hydrogen and another nonmetal. A common example of polar covalent bonds is with water, otherwise known as H2O. Now let's say this iron block right here represents oxygen, and these gray blocks represent hydrogen. So the electronegativity of oxygen is 3.44, and hydrogen is 2.20, and that brings the difference to about 1.24, which is well within the range for a polar covalent bond. And indeed, that is what happened. We also see the inequality of electron distribution here, which explains why the molecule is shaped in the way it is, which is bent, like a V shape, but that's for a later video. Now we have a polar covalent bond, where oxygen has a net negative charge and hydrogen has a net positive. It's like a big dog and a small dog or two, and they play tug of war.
Really loving the dog analogies here, Dave. Now it's time to move on to intermolecular forces. Let's start with dipole-dipole forces. In essence, dipole-dipole forces are attractive forces between the positive end of one polar molecule and the negative end of another. Remember those polar covalent bonds we just talked about? Well, since one side has a greater electronegativity than the other, you end up with one positive side and one negative side of the molecule. Consider these the poles of the molecule, if you will. With one positive pole and one negative pole, it only makes sense if the positive pole of one molecule is attracted to the negative pole of another. As you can see here, we have two molecules that are bonded together with their intramolecular forces. And then here, in between these would be the intermolecular bond, where the positive end of one molecule is attracted to the negative end of another.
Now that's just brilliant, Jeanette. Just brilliant. Now on to London dispersion forces. If you would just come over here. Thank you very much. Now, electrons orbit around the nucleus like so. That's a given. Just pretend these are orbiting instead of just standing still. And they go around and around like so. But if the outer electrons happen to be on one side of the nucleus, like so, just get rid of that and ignore this extra length bond right here, like so, then what will happen for an instantaneously, is that they will have a chance to repel their neighboring atoms over to the other side of their neighboring nucleus, like so. And because of that, you end up with a positive nuclei next to a negative nuclei, next to one side of the electrons, and then they come together in an electrostatic attraction. It's the forces caused by the mutual instantaneous polarization of atoms. It's a very weak bond and will last for only a second, like so. But then the electrons soon go back to orbiting around their nucleus, waiting for this to happen again and again. And it's based purely on luck, and if everything goes perfect. An example is where you spin a wheel with a dog on it, and if everything goes perfect, you win.
You know, that was an interesting dog analogy. I don't know about that one. But next is hydrogen bonding. Remember how just before this we were talking about dipole-dipole forces and how they're the bond between two molecules that have two distinct sides in terms of electronegativity? Well, let's take it a step further. Going back to my nice little demonstration way over here, way over there, let's pretend that those two molecules were water. So, as soon as I get over there, here we go. Let's say that this here is oxygen, and we've got two hydrogens right here, right? Well, you'd think that because of this and another oxygen, hydrogen, water molecule, you would have dipole-dipole forces, but actually, these two here are bonded together through hydrogen bonds, which are a little bit different and a little bit stronger. They're a specific type of dipole-dipole force that is made up of a hydrogen atom, a more electronegative atom, such as nitrogen, oxygen, or fluorine, and another adjacent atom bearing a lone pair of electrons. Naph or Phon can be used to remember which specific atoms are seen in a hydrogen bond. But remember, hydrogen bonds are not the bonds that connect the hydrogen to the naph, but instead the bond in between this here and another molecule. The molecule containing the hydrogen and nitrogen, oxygen, or fluorine is stronger than other typical dipole molecules and attracts other molecules more easily. Super simple.
Now, Jeanette, that is truly a masterpiece. But now it's time for my masterpiece, which is metallic bonding. Can I get a yay for these tutors?
Woohoo!
So, metallic bonding is another intramolecular force. Now, anyway, in the 1900s, old man Paul Drude, this man, we'll call this man Paul. Hello,
Very
Paul.
nice.
He came up with the sea of electrons theory, which models metals as a mixture of atomic cores, which are the nuclei and inner electron shell, and valence electrons. It's basically a bulk of metal atoms all together joined by metallic bonding. It's a very strong type of bond, which it can be reinforced by metals generally having higher melting and boiling points than other atoms on the periodic table. As you can see, I am trying to light this tank on fire and it's not working. So they are surrounded by 8 other metals, and all the valence electrons overlap to give a vast number of molecular orbitals which extend over the entire metal. As you can see in here, we will have the 2 electrons be this fish tank, and the electrons be the turtles. And these light blocks, called glowstone, are the positive nuclei. So now the electrons can move freely within these molecular orbitals, and because of this, each electron becomes detached from their parent atoms and is deemed delocalized. As you can see, these fishes are swimming around. Now, turtles are fish. So now, we have a sea of delocalized electrons with a vast number of molecular orbitals. Now, the metal is held together by the strong forces between this sea of delocalized electrons and the positive nuclei, which causes a strong bond but still allows metal to be malleable, unlike in comparison to ionic bonding. As you can remember with ionic bonding, there was a fixed lattice that's hard to mold and shape however you wish, whereas this sea allows the shaping of metal to be much easier than breaking or melting it. An example can be with a pack of dogs, stronger together, but they move around, trading jobs, huddling for warmth, and the works.
Of course. Way to tie it together with another wolf-dog analogy. Well, I've got one more for you. Let's see. You know what? Never mind. For the sake of time, we're going to cut it there. Thank you, guys. I think that's plenty of
It's
dogs.
a pack of dogs.
Plenty of dogs. That brings our video to a close, concluding our topic for review project.
And that concludes. We'll see you next time. This is Dave.
And this is Jeanette. Until